Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. We are looking at Chapter 5 on thermodynamic processes and cycles. And in this lesson, we're going to be looking at how we can modify the basic Rankine cycle in a way that might improve the thermal efficiency. What we want to do is consider ways that we could change the operating conditions and make the cycle better. So the problem statement told us a pressure and temperature, but we actually could have had choice in that if we were doing a design of a cycle, right? Now the purpose of the power cycle is to create power out of the turbine. And basically what we're doing is we're converting the energy contained by the fluid into work. We start at a high temperature and pressure, and we keep pulling energy out of that fluid through a turbine by turning those turbine blades. And we do that until we have as much work as we think we can realistically get out of it, okay? So what if we didn't stop where we did before, but we have actually dropped that lower pressure even lower, okay? That actually will increase the work out of the turbine. You are going to have to compensate for that, though, because now that's going to put a larger burden on the pump, okay? But net, you should still come out ahead. You should still produce more net work. And this isn't going to change the heat transfer for the boiler. So that will definitely increase the thermal efficiency. But unfortunately, there are practical limits, okay? The reality is that as you decrease the pressure coming out of the turbine, leave the material basically in the turbine longer, turning those blades just that little bit longer, what's going to happen is you're going to start forming liquid droplets. And once that happens, you're going to destroy the turbine blades. So therefore, we want to always make sure that we have a quality coming out of the turbine that is a minimum of 90% for our ideal Rankine cycle. Now we'll come back and look at this a little bit more later. But basically, we want to always choose a pressure that's going to keep Q2, the quality at state 2, greater than 90%. Okay? So you can go down that low, but you can't go down indefinitely low. Well, what happened if you were to superheat the steam in the boiler? Okay, so another way to do this would be to have more energy in the material as it goes into the boiler. So let's just make it hotter, okay? Well, if it's at a higher temperature at the same pressure, it will indeed produce more power, okay? Unfortunately, to get it to that higher temperature requires more heat transfer into the boiler. Now, you're paying for the fuel for that. The reality is you usually don't win at this game. This actually typically lowers the thermal efficiency. The denominator in the thermal efficiency, right, it's net work over heat transfer at the boiler. The denominator tends to grow faster than the numerator, so you actually lower the thermal efficiency. People do this, however, but the reason is not to increase efficiency. The reason typically is to protect turbine blades. This could be done by the initial design, but sometimes it's done in a working plant where they discover that they are starting to have these liquid droplets forming, okay, and get pitting on the blades, which is basically eating away at them slowly. And if that happens, a fix that you can take that is not too difficult is to bump up the heat input into the boiler. Yes, it's going to harm your thermal efficiency, but it will protect your equipment. A last basic modification you might make is, well, okay, if I want more energy at the inlet, just bump up the pressure, okay? Yes, indeed, you will have higher pressure, which if you take it even just to saturated steam, will guarantee that you have more energy going into the turbine, which will increase the amount of work. Okay? But it's also going to require more work at the pump, and it's going to probably require more work or more heat transfer at the boiler. You may win this game, you may not. The gains here tend to be modest. That, yeah, you can increase the thermal efficiency, but going from 33.2 to 33.4% may not really be worth the extra energy that you're putting into it. Another thing about this is when you do this, that lower pressure now needs to really be examined, because you could fall into the trap of dropping your exit pressure to the point where you now have that quality below 90%, where you're getting the pitting of those blades, destroying your equipment. So these were some simple modifications we could do. In our next lesson, we're going to come back and we're going to look at maybe some equipment modifications we might make to improve our cycle. Thank you very much for your time.